is just a fixed number. It's possible that when you interchange two particles, that the wave function should pick up a phase. On the other hand, supposing you do it twice, supposing you interchange x1 and x2, and you say, when I interchange x1 and x2, the wave function should get multiplied by the phase, and then you do it again. You interchange them again. You get back to the same place. You get back to the same place. You get back to the same state that you started with. In other words, when you interchange twice, you really do have to come back to the same thing. No other possibility. So the general guess would be that e to the I phi here is either plus or minus 1. It's an operation. When you do it twice, you get 1. But there are two possibilities. There are two sensible possibilities. Well, you might say only one sensible possibility, but then you'd be leaving out half the particles in the world. Plus, bosons, particles which satisfy that property, that when you interchange any two of them, and in fact it could be a multi-particle state where you just take any two and interchange them, if the state is exactly the same, then they're called bosons. So bosons satisfy the property that the wave function or the state vector, when you interchange any two of them, stays the same. Fermions are the case with a minus sign. Okay, so when you switch two fermions, identical fermions, the state vector changes sign, keeping in mind that the change of sign is itself not observable. It's not an observable thing because the probability distributions, expectation values, everything of interest involves psi times psi star. Alright, so if the state vectors change in this way, then the same must be true of the wave functions. For example, let's take x1, x2 psi. That's by definition psi of x1 and x2. Whoops. Wave function of particle 1 and particle 2. On the other hand, it's x2, x1. That's equal to psi of x2, x1. In other words, the two wave functions are related to each other just by switching the arguments. But now, if the state vectors themselves have this property that they either change sign or don't change sign, then the wave functions must have the same property. So this becomes a property of wave functions. And let's write it down. If you have a wave function for fermions, a system of fermions, x1, and now let's just do it for two particles, and then I'll tell you what to do for many particles. The rule is, for fermions, it must be equal to minus what you would get if you interchange the particles. When you interchange the particles, the wave function changes sign for fermions. What about bosons? For bosons, no change of sign. Plus. Okay, let's think about some states and see what sense we can make out of this. Supposing let's take a case of bosons first. The case of bosons is a little simpler. no change in sign. Let's suppose we have two bosons in two different states. Well, one state could be, let's again forgetting spin. One state could correspond to some particular wave. It doesn't have to be an atom, incidentally. It could just be any system. But let's take some of these atomic states here. Okay. This wave function, or the wave function associated with this state here, could be called size 0, let's call it. 0 because it has zero angular momentum and because it's the lowest energy state. All right, so we're going to put particle 1 into that state. So the wave function of particle 1 would be size 0 of x1. Let's put the next particle in some other state. It could have the same angular momentum or a different angular momentum, but let's make it a different state. Let's make it a different state. Well, let's first do the case where we put the particles into the same state. Oh. Let's put two particles into the same state. Then the state vector would be size 0 of x2. Particle 1 in the state size 0, particle 2 in the state size 0. Does this satisfy the rule for fermions? Does it satisfy the rule for bosons? Well, this structure here is obviously unchanged if you interchange 1 and 2. It doesn't matter which order you multiply wave functions. Wave functions are just have numerical values. They're not operators, they commute. Okay, so this wave function here, two particles in the same state, that's symmetric. The word is symmetric. Symmetric under interchange of the two arguments of the wave function. It does not change sign. So if such a wave function makes any sense, it makes sense only for bosons. For fermions, this is not possible because this does not satisfy the rule for fermions. Okay, let's try another state. And another way of saying it is you can only put bosons into the same state. Two bosons into the same state. Okay, let's take one particle and put it into size 0, and the other particle put it into another state which I'll call psi 1. Okay. What happens if I interchange 1 and 2? Not 0 and 1, but what happens if I interchange x1 and x2? This will become psi 0 of x2, psi 1 of x1. In general, if these are two different wave functions, the left side and the right side will neither be equal to each other nor equal to their negative. Just product of two functions. Sine of x1 times hyperbolic moose of x2. That has no symmetry whatever. It doesn't change sign or it doesn't stay the same. So this is not a possible wave function for either fermions or bosons. Does that mean you can't put one particle into one state and another particle into another state? Not quite. Let me now take a state which is made by taking both of these combinations here and adding them. This is a wave function, perfectly good wave function. It's a superposition of particle 1 being in size 0, particle 2 being in psi 1, and the opposite, particle 2 being in psi. But both of them have a particle in size 0 and a particle in psi 1. They both